Now we're ready for the mean value theorem. We just talked about Rolle's theorem. That's a special case of the mean value theorem. The mean value theorem guarantees for that a function that is continuous and differentiable, continuous on a closed interval, of course, differentiable on an open interval, again, just like before. Then, this is my conclusion right away. If it's continuous and differentiable, there will be a point C in AB such that f prime of C is equal to f of A minus f of B. I'm sorry, I said that backwards. F of B minus f of A over B minus A. Okay, what is that? So first of all, let's look at this picture. So I've got my nice continuous differentiable function, and I have a f of A and f of B value. If I calculate this ordered pair here is the ordered pair A comma f of A, and this ordered pair here is the ordered pair B comma f of B, and that's just the slope, right? y2 minus y1 over x2 minus x1, that's just the slope. Okay, so what it's saying is that the slope between those 2 points will be realized at another point in the interval. Okay. Now, if you look back at Rolle's theorem, that's just a special case because the slope between those 2 points is just 0. It's saying that that slope of 0 is realized between them. The mean value theorem generalizes that and says it's true for any slope, not just slope 0. No matter what the slope is, I'm going to have a point between them where that slope is also the same, it's realized. Now again, there could be more than one. It looks like there's another one right here or so that would have that same slope. So this one has a C1 and a C2 as well. The mean value theorem guarantees the existence of at least one. There could be more than one. Okay. Some applications of the mean value theorem. There's some position and velocity interpretations. The average velocity over an interval is equal to the instantaneous velocity at some point within the interval. So instantaneous velocity can be hard to compute, but if we can find the average velocity, we can guarantee that it's achieved at least one point in the interval. We can also talk about it in terms of velocity and acceleration. We can find average acceleration, it's just slope, so relatively easily, and your average acceleration must be achieved as instantaneous acceleration at least some point. We'll look at those applications in a little bit. Okay, first, in part 3, we're going to sketch a secant line to the graph through these 2 points, then sketch all lines tangent to the graph for each x value guaranteed. Let me find a ruler real quick. Alright, I got a little ruler here, so let's draw some lines. Alright, so the first line that we drew just connected A and B, f of A and f of B. So this is our secant. There should be, because this is a continuous and differentiable function, because it's smooth and connected, there should be at least one point that has this same slope as a tangent. So if I try to push this up without changing its direction, so let's see if we can find a line that's tangent. There seems to be one right up here. So this would be a point where I have a tangent that has parallel to the secant. So I've got a C value right there. Okay, those are hopefully parallel. And then if I draw down, I can say there's another one right here. Oops. Accidentally tipped that a little bit. Another tangent that's parallel to that secant. So I actually have 2 of them in this case as well, as C1 and a C2. There are 2 points whose tangent slopes are parallel to the secant slope through A and B. Okay, so those were the 2 initial points. Between them, there are 2 points who have a tangent slope that is the same. Alright, so I was just about sketching, looking at that visually. In example 4, we wanted to explain why the mean value theorem does not apply to this function. Well, the two conditions of the mean value theorem are continuous and differentiable, and this function fails condition 1. It's not continuous. Not continuous at x equals -1, so not continuous on the interval -5 to 4. Had they asked me if the mean value theorem applied on the interval 0 to 5, or 0 to 4, I meant to say, 0 to 4, I would have said yes, because on 0 to 4 it is continuous. But because -1 is in that interval, it's not continuous, and so the mean value theorem does not apply. In the next one, we're going to determine analytically whether the mean value theorem applies for this function, and if so, we'll find the points guaranteed to exist by it. Okay, so there are only two conditions I need to show for the mean value theorem. First is continuous, so we got to get domain. Okay, so domain of f is, you got to be less than 2. So it's -infinity to 2. So we can conclude that therefore f of x is continuous on, our interval is -7 to 2, because that's a subset of the domain. Second, differentiable. Got to find the derivative to talk about differentiability. Okay, so the derivative is 1/2 2 minus x to the -1/2. Derivative of the inside, -1. So that's -1 over 2 times, I'm going to write that as a square root of 2 minus x in the denominator. Okay, I know I can't have -2 because it makes the denominator 0. The domain of the derivative is -infinity up to 2 parentheses. Domain of the derivative, f prime, is all real numbers up to but not including 2, parenthesis. So that means that therefore f of x is differentiable, which just means that the derivative exists, on -7 to 2. It has to exist between -7 and 2, and it does because it exists everywhere less than 2. Okay, so before I can state my conclusion, since the conclusion here is not going to involve just derivative equals 0, it's derivative equals secant slope, I need to find the secant slope. So let's first find f of -7 and f of 2, because those are the endpoints of my interval. Into the original, f of -7 is square root of 2 minus -7, that's 9, so that's 3, and f of 2 is 0. So if I find the slope, the secant slope is going to be 3 minus 0 over -7 minus 2, so 3 over -9, or -1/3. Okay, so I can conclude now, since condition 1 and condition 2 were satisfied. Thus, there exists a c in the interval -7 to 2 open, such that f prime of c is equal to -1/3. Okay, that's our conclusion. If you want to see that conclusion written out in words, I can do that as well. Thus, or therefore, there exists a c in the interval -7 to 2, such that f prime of c is equal to the -1/3. Same thing. Okay, I found the -1/3 by finding the secant slope. That's just the slope. I had to find the y coordinates. I already knew the two x's, but I had to find their y coordinates. So I could just do regular slope right there. Okay. So we've guaranteed its existence. Sometimes that's all I need to do. I've done the first part, determined analytically whether it applies. It does apply. Then I'm told that if so, find the point guaranteed to exist. Okay? Now we're going to find it. So we're finding a point where the derivative is equal to negative 1/3. I've already found the derivative. So f prime of c equals negative 1/3. The derivative is negative 1 over 2 square root of 2 minus x equals negative 1 over 3. If I cross multiply, negative 3 equals negative 2 square root of 2 minus x. Divide off the negatives, divide off the 2. 3 halves equals square root of 2 minus x. Square both sides, 9/4 equals 2 minus x. Add the x, subtract the 9/4. X equals 2 minus 9/4. 2 is 8/4 minus 9/4 is negative 1/4. So it needs to be at negative 1/4. Okay? So f prime of negative 1/4 is equal to negative 1/3. So the c value is negative 1/4. That's our conclusion. Now we're going to check out this graphically. The first thing I want to do graphically is connect my two endpoints. Hopefully this has a slope of negative 1/3. The scale on this is a little strange. Notice it's counting up by halves and over by ones. So we'll have to trust that that is a negative 1/3. This would be down 1 over 1, 2, 3. Yeah, that looks like negative 1/3. And then trying to very carefully draw a parallel line that is tangent. Hopefully it looks reasonable that it's going to have an x-coordinate at negative 1/4. Now I can do a little better job of that on Desmos, checking that real quick. But I think I'm out of time for this video, so I'll check that in a second.